All right, so let's run through the quiz first, and then we can talk about homework, and then we'll go back to proofs. So quiz, question 1, I think everybody got question 1 other than a typo here or there. So union of sets, right, is the collection of all the sets taken together. And you only count things once, you're not allowed to count them twice. Intersection is things that are in both sets, so that's the overlap. So the union of A and B is just 1, 3, 5, 7. The intersection is 3, 5, 7. And then A take away B, start with A, and throw away everything that's in B. So you have 1, 3, 5, 7, throw away 3, 5, 7. So part C, the answer is just the singleton set 1. So I didn't see a lot of issues with that. So question 2, proving using a membership table. So membership table is different from a Venn diagram, and it's different from showing this for a particular case. So membership tables are basically truth tables. So we have 3 sets involved, A, B, and C. And everything can be either not a member or a member of each set. And I usually just break these up in groups of 4 to help them line up better. And we're trying to prove this identity. So this is distribution of a union across an intersection. So how do you do this with membership table? We're basically going to write a column for each side and show that in all cases those columns have the same values. So I like to work in pieces. Let's do B intersect C first. And so this is a logical AND operation. It's saying if something's not a member of B and is not a member of C, it can't be in the intersection. If it's only in C, it can't be in the intersection. If it's only in B, it can't be in the intersection. But if some element is in B and it's in C, then, and exactly then, it is in the intersection. So we can fill this in the way we would a logical AND of B and C. And then we can take A and union it with that prior column. So this intersection column union with A. So if the element is in either A or in this intersection, then it's going to be in the union of A with the intersection. So these will be 0s and 1s, and these last 4 rows, since the element's in A, it's certainly an A union something. And then you work out the right side, so A union B is an OR. A union C is another OR. And then intersect those. So look where you have 2 1s in these 2 columns. So now we've got truth tables for the left and right side. And we just need to observe that this is exactly the same as that. So whatever element you pick in the universe is going to belong to this set exactly when it also belongs to that set. And if it belongs to that set, it's going to belong to this set. Well, that's the definition of set equality. So the equality of each row of this truth table is enough to say this set's equal to that. That proves the identity. All right, question 3 we talked about after the exam. Question 4, so given a compound proposition, let's write it in terms of simpler propositions. So if it's sunny, then I'm running outside, so we may do something like let P be the proposition which says it is sunny. and let Q be the proposition, which says I am running outside. So our original statement says, if it's sunny, then I am raining outside. If it is sunny, then I am running outside. So that's just if P, then Q. And then we're asked for the converse. And the converse, just switch around the hypothesis and conclusion. That's Q implies P. If I'm running outside, then it's sunny. The inverse, we take the original and we just negate each side. If it's not sunny outside, then I'm not running. And the contrapositive, we flip the order and we also negate them. So not Q implies not P. That's the inverse. This is the contrapositive. And this one is logically equivalent to the original statement. The converse and the inverse could also be true or false, but they're not equivalent to if P then Q. All right, and then question 5 is looking for a direct or an indirect proof of the following theorem. So not Q, P implies Q, P or T. All of that implies T. And did we already prove this last time? Okay. So so the issues I saw in here were either what seemed to be missing steps, where somebody might write P or T and then say therefore T, but they never proved anything about P. And T does not follow directly from P or T, right? It'll follow from P or T and the idea that P is false, right? So you can argue this with a little bit of work. But it seemed like there were some missing steps in some cases. I also saw a few cases where you use T as part of the proof. And if you're assuming T is true, that's okay, but whatever comes after that, you cannot prove that T is true, right? If T is an assumption, you can prove other things, but you can't somehow magically say, therefore T is true, because you already assumed it was true, right? And everything that comes after this relies on knowing that T is true. Well, if you eventually prove T, that's true only if T is true. Right, and that's just a tautology. If T is true, then T is true. So you really got to be careful not to put this in your proof. But the one thing you can do that kind of looks like that is if you do an indirect proof, right? If you assume not T, well then you better not be able to prove T, right? But you can argue and you can prove some kind of contradiction, and then come back and say this is false and therefore T is true. So if you're not sure what was wrong with your proof for number 5, talk to me at the break or something, and let's go over it, because we're going to be doing proofs for the next couple of weeks, and then we'll be using them throughout the rest of the course. All right, so homework questions. Yeah.
Can you talk about the difference between the conditional, the implication, and equivalence? Two tables.
Sorry, what were those 3? Conditional?
Yeah, the conditional, the implication, which is like the double line arrow.
Okay. And what's the last one?
And then equivalence.
Equivalence, like that?
Yeah.
Good, yeah, so conditional, if proposition P is true, then proposition Q is true, and we usually write it like this. Okay, that's a conditional statement, or an implication. This is very similar It's more kind of a notational difference. When we have a bunch of things listed, and then we have this, right? It's almost just like a hierarchy. It's saying that all of this implies that. And if you group all of this in parentheses, it's really no different from that.
Okay, so if you wanted to write it on a truth table, then it would be essentially the same as the conditional.
Yeah, yeah.
Okay.
Now, equivalence is really saying that these two things on both sides are simultaneously true or false. They have the same value, which means logically they're saying exactly the same thing. And I think that might be interchangeable with that. But we really think of it as just saying, like, they have the same truth table values in all cases.
Okay, and then conditional, it's only false if P is false.
Conditional is only saying if P is true, then Q has to be true. Right? So if P is false, this is automatically true. If Q is true, this is automatically true. The only time it fails is if P is true and Q turns out to not be true. Then the conditional is false.
But don't you use the double arrow when you have all T's below the double arrow? In other words, if you build a truth table for that, then the double arrow indicates that the final column for the implication is all T's.
So truth table for this whole thing?
Well, the double arrow indicates that the single arrow has all T's underneath the double arrow. Or underneath the single arrow when you build a truth table for the single arrow. That's what I understood a tautology was. And the double arrow indicates the implication when you build a truth table for it is a tautology, so that.
Yeah, this is not a tautology.
Well, but that's what I thought the double arrow meant. No, the single arrow is not a tautology.
Neither is the double.
Well, by the basic definition, but you could have a complicated set of, like you said, all those squiggles.
Mm-hmm.
And all those squiggles together, when you did a truth table and put the final column underneath the single line, the single arrow, it could be all T's. And if that's all T's, then that's what indicates that the double arrow, that when we use the double arrow, is that the single arrow has.
Can you show me at a break what you mean by a truth table for this? Because I'm not sure where the T's are going.
Well, I'm just saying the final column of.
So let's do this. P implies Q implies Q. Right. So that's a true theorem.
So build your truth table with P and Q up front.
Right.
And then build a truth table for P implies P conditional Q.
Mm-hmm.
And then do it for the whole statement that you've written above. P and P implies Q.
So let me do it for this first. This is really a conjunction, right?
Well,
This is saying that P is true and P implies Q is true.
okay, so then is that, I'm just, I can't read your writing. Is that, what's that?
False, 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 true.
No, but I mean the header of the column. Is
P, comma, P implies
that,
Q.
Oh, comma, okay. P and P.
Right, so these are going to be true because the hypothesis is false. And here the hypothesis is true and the conclusion is true. So this is true in all cases.
So, right, so because you have, see, the way I would do it is you don't put a double arrow. You don't put a double arrow where you've got the double arrow, you put a single arrow. And because that
Right here?
no, down below in the table, on the right-hand column, where you've got a double arrow,
Yeah.
make that a single arrow.
Okay.
Now, because that final column has all T's, then we can write the double arrow. That's the definition of the double arrow, I thought. was you get all T's down that final column.
Okay, I think that's always going to have all T's if you do this for a theorem.
If it's a true theorem, but
Yeah,
if it's not
yeah.
a true theorem, if it's not a true theorem, if you don't get all T's down there, then you can't write the double arrow. That's the way I understood it. If I'm wrong,
Right. Yeah, the double arrow is saying that this implies that.
but what does that mean? It means that there's all T's down that final column.
I see what you're saying. So it's more than just an if-then, it's an if-then that is always true.
Exactly.
Okay. I'm okay with that.
Okay, I just thought that's what it was.
Yeah.
So why is the second row true?
The second row?
Column, you mean?
Yeah. Because the first statement is false, and then
So if the first thing is false, it doesn't matter what the second thing is. Right? A conditional, if the hypothesis is false, it doesn't matter what the conclusion is, the conditional is always true. That's a separate.
That comma is really just an and.
Yeah. Right? If the hypothesis is false and the conclusion is false, technically the statement if P then Q is considered true.
right.
Okay. If the hypothesis is false and the conclusion happens to be true anyway, right, this is still considered to be true. So that's the second column, right, or the second row. So the conditional is true. This is saying that P is true and P implies Q is true while P is false, so this is false. So this whole thing is false, so saying that this implies Q is true, right? It's exactly this case.
I think that's the part I don't understand.
Okay, let me do it like this. Triangle, square. If this is false and this is true, then triangle implies square is true, right? Okay, so this is my triangle, and this is my square. This column is saying P comma P implies Q implies Q. It's saying this column implies that column. So if this column is false and that column is true, then the implication is true.
I think I'll just come in after class.
Okay. It may be one of those things where if you kind of blindly plug this and this into your truth table for if triangle and square, it's true. Yeah, we can go over it at break. All right, other questions?
Could we go over 3.5 number 6? I know we did an example of it in class.
Yeah, so we were talking about this one earlier too. So Randy and I were just talking about this before class. This may be a poorly placed problem in the book. A lot of it is red herring. The real punchline is students who do well in courses do not skip classes. We're told that that's true, right? And then we're asked to prove that students who do well in a discrete math course do not skip class. And it looks like the only way you can actually get that is by looking at that second statement. Students who do well in courses do not skip class. And understanding that discrete math course is a course. And so we know that if they do well in courses, they do not skip classes. And so the conclusion we're trying to prove is that if they do well in discrete math course, well, that's a course, and we've been told if they do well in a course, they don't skip classes. So it seems like that follows from the second hypothesis, but not really until we talk about what are called quantifiers. This idea of for all of something or there exists a something. And so unless I'm missing something, I feel like this should have come in a later chapter after section 3.8 was covered. So I think it's a confusing question. Anything else?
Can you do 3.4, number 2?
3.4b, so direct and indirect proofs. So P implies not Q, not R implies Q.
I'm sorry, 3.4.
Oh, section 3.4.
Yeah, sorry.
It's okay. 3.4, number 2. Show the common fallacy is not a law of logic.
And that one we didn't have 2 proofs for.
All you got to do is find a counterexample, and that will be a sufficient demonstration.
Or we could use truth table.
You could use a truth table. You can use an example.
So what would that look like if you did a truth table for it?
Oh, let's see. So there's P, there's Q. Here's P implies Q. Here's not P. Here's P implies Q and not P. So the end of these 2 columns.
I think you're not P might be wrong. Should we choose from both sides?
Thank you. Alright, so the end of those is true, true, false, false. And then P implies Q and not P. I need one more column, which is not Q, which is true, false, true, false. So then does this imply that? True, true, yes, true, false, no. False, true, false, false. So this is not always true. It fails to be true exactly in the case when P is false and Q is true. And that can help you find an example. Let P be the proposition x equals 2, let Q be the proposition x squared equals 4. And suppose x equals -2. So if x equals 2, then x squared equals 4. That's absolutely true, right? So this is definitely true. And since x is -2, x is not equal to +2, so not P is true. So this is also true. So this is true and that is true. This theorem says therefore Q is not true, which says therefore x squared is not 4. But that's false. X is -2, x squared is 4. So there's an example where the left side is true and the right side still fails to be true. So that's enough to say this is not a logical conclusion. Other questions?
If you have time, can you do 3.5, 2A?
2A? Prove with truth tables? Okay, let's see. This is a sneaky one. Okay, so prove Q, not Q implies P. So let's make our truth table. And let's make a column for not Q. And then Q, not Q. So this means Q is true and not Q is true. Well, that's false, that's false, that's false, that's false. This is never true. Right, it's false in all cases. Let's write down P again just to have it over here. And now let's write down Q, not Q implies P. All right, let me just draw this as a single arrow, just a plain old implication. So just looking at these two columns, let's fill in the truth table for implication. Well, if the hypothesis is false, the implication is always true. Right, so this is true in all cases. And so no matter what the value of P and Q are, this statement is true. That's a quirky one.
I think what I get confused is that it's an implication, not an equivalence. We're not trying to find if it matches P, and sometimes I think.
Yeah, we're not showing that they're the same thing.
Yeah.
Right, we're showing that the thing on the left implies the thing on the right. And in fact, they're not the same thing in this case. So we couldn't write, you know, triple equal sign between them. All right, so let's dig deeper into proofs. So I think I already gave this definition, but let's write it down again. An integer n is even if n equals 2 times I, where I is an integer. So for some I, which is an integer, n is equal to twice that integer. So an even number is divisible by 2, basically, in the sense that if you divide by 2, you get a whole number. And an integer n is odd if it can be written as 2i plus 1, where I is an integer. Or if you like, if it's one more than an even number. So let's prove if n is even, then n squared is also even. So the square of an even number is even. So step one, I'm going to say n is even. And why do I know that n is even? Well, I don't. That's my hypothesis. I'm not going to prove that n is even. That's impossible. I'm going to prove that if n is even, then n squared is even. So I'm going to assume the hypothesis is true, n is even. I'm going to argue logically, and I'm going to hopefully conclude n squared is even. But it's only going to follow from this assumption, this hypothesis, that n is even. Okay, if n is even, there's really nothing we can do but plug in the definition. So n equals 2i, I is an integer. That's the definition of even. So n is twice some integer. And I'm trying to make a statement about n squared, and I'm almost out of things I can do. So out of desperation, I'm just going to square this version of n and see what happens. So if n is 2i, nobody can argue that n squared equals 2i squared. And that's 4 times the quantity I squared. And that's just algebra. Now, if we know that n squared is 4 times I squared, how can we use that to conclude that n squared is an even number? Yeah. So that's just pulling out a 2. And you probably don't need to make this a separate statement. You need to say it somewhere, but 2i squared is an integer. And I'm just going to say properties of integers. So if we have an integer and we square it and we multiply by 2, we're still going to get an integer. Well, n squared is therefore 2 times an integer. And since it's 2 times something in z, we can conclude n squared is even. That's the definition of even. And it's looking at statements 4 and 5. And so that's the end of your proof. Does that seem reasonable? All right, so find 1 or 2 people to work with, hop onto the board. Well, I'll leave this up here. But here's what I want you to prove. If n is odd, then n squared is odd. And it's a similar proof to what we just did. So we're starting off with n being an odd number, trying to prove its square is odd. So find a spot on the board, find some people to work with, and see if you can make a stab at proof of this.
We have an error over. We said everywhere. Why? There you go, we're assuming.
Yeah, you can use those definitions.
You just start by squaring in.
What's the definition?
If we just call this from this.
And what is the definition of this? Like this.
I'll write that. And it all.
There's some number here. It equals two times some number plus.
Yeah.
Same kind of thing as that specific example. Somebody gave us all the bad pens. Where
We
the,
got a bunch to choose from.
where the distinct is.
Give me the ones that are dead.
Variable, it's a value that is then element in.
I think they would distinct disadvantage.
So this.
Yeah, the front board.
And the hierarchy because it votes in
It's also been
an
one
element
vote.
of code. So there's no parameter for it.
It was the
It's just right here. So you're saying like if this is an element of the integers plus one, then it's on. If you just said this is equal to x, then x will automatically
You want to make sure that it's an even,
the x plus one.
and then you want to add one to the even. So how do you make sure how do you make sure something is an even?
So you can't with this.
You just say.
So where's the definition of odd for insecurity?
So it would be this.
Now, at that point, it is even, right? But if you want to make it odd, what do you do?
You add one.
You add one. And then you have to say out here, or some k, some k.
N squared and integer plus one.
K is an integer, that's right.
You gotta make it odd. And an integer plus one also.
Oh, yeah, there are two out.
There you go. Look at
Yeah, you just pull two, so it'd be
No,
two out squared.
the variables only have to be. Okay, so now, we know it is odd, so that, we know that's true. So now what we're supposed to do is in square.
Yeah.
Yeah. Two would have to be right.
It'll be odd.
So, yeah, we have to show that n squared is odd. So let's first find out what n squared is equal to. So square looks like.
Right. You said n squared is 2 times 2i squared.
Two
Okay, so now, right, look at the right hand side, it's just binomial squared.
But you don't want to include this in the
Wait,
definition.
wait.
Because you use this as the definition of saying.
Oh, sorry, I thought we
So
were.
what he's saying,
I thought we were
he's saying is like, if we say this, that would just be this, so then let's just say like, let's just say 4i
Okay.
squared plus
That
4i
works.
for each of the x.
Or just multiply the binomial squared. And then
So then we just have x squared,
yeah, just multiply that for power of one.
that'd be on the thing, but you can put 10 in
N
there.
squared is still equal to that.
Or you could say 10 is an 9 is an intro. Yeah, he's saying that 10. So if you say plus 1 squared I, squared plus 2i, then there's still 2 here, then 2 equals b. 4 big. Like that. So then you say that's equal to x. So then you have there, 162 times.
See, if you do it, you're leaving in terms of
Not true.
what's 2 kilos and 4.
There's no integer because x is an integer.
Okay, we'll give you a.
You plug in 4, you get 8 plus 1.
This is 2. So you got.
And if you plug in 5, you get 10 plus 1.
Oh,
You can't make
I see.
this 10 is
We'll just. It's totally like 4 and 5 now, but I think you skipped step 3 and 4.
Okay.
So what you had written before.
Oh, yeah, I was just showing them.
You want to.
But this is really what you need. What you had before wouldn't actually,
Added to something that's equal.
Wait for your
How can we
right.
prove that's even?
if you don't actually take it into this form, because this is showing that n squared is 2 times an integer plus 1. That's what you need to say n squared is odd.
N
Right.
squared
So
equals.
you gotta have it factored like that. But then you probably still need this previous step where you say n squared is 4i squared plus 2i plus 1, and then pull it out for that. And then you got it.
parentheses.
Makes
That's
sense.
the one.
Cool.
So that does not say that. In the clear is equal to an even plus 1. So that must be done.
All right, cool. So let's do a 5-minute break, and then we'll look at a different version of this. We'll look at the converse.